Well, hi there, and welcome from Studio 27 in Sacramento, California, to today's webinar, Hybrid Positioning and Technologies for Mobile Users, sponsored by Spirent and Inside GNSS, and hosted by WebAttract, your end-to-end solution provider for informational webinars. Hi, I'm Mike Agron. I'm the executive webinar producer with WebAttract, and I'll be your moderator and one of your hosts for today's session. In just a second, I'm going to be introducing a fabulous panel of thought leaders to today's webinar, and we're going to hear from these experts as they discuss groundbreaking technologies that can be integrated into mobile devices to ensure accurate and uninterrupted continuous positioning capabilities despite location or surroundings. Now, you're also going to have the opportunity to have your questions answered at not only the end of the presentation, but at the middle, and I'll tell you all about that during our Ask the Experts panel session, and I'll tell you how to do that. But for now, let's get started, as we have quite a bit to cover. We have quite an interesting audience. There are over 850 professionals like yourself that have registered from over 59 countries, 34 states and provinces, and as you can see, you represent the following industries. A majority of you are in other industries, but 20% are in product application designer, system integrator, mobile device manufacturer, or GNSS equipment manufacturer. And what we're going to talk about today is best practices and examples that illustrate how the technologies can work together in producing outcomes that keep pace with the increasing reliance on position location functionality and the decreasing tolerance for gaps in services. Now, over the next 90 minutes, and note that this is a special webinar of 90 minutes, we're absolutely confident that regardless of your industry segment or role, you're going to find value in what we have to present today. Well, let's get to our first poll. So if everybody will take a look at their screen, I went ahead and launched this. Choose one. Let us know, GNSS alone will not provide sufficient accuracy and availability even when GLONASS, Galileo, and Compass are fully operational. Choose one. Do you agree? Do you disagree? Or you're not sure? And let's share the results. So 65% of you agree that it will not provide sufficient accuracy. 14% disagree. 20% you're not sure. Well, that's terrific. You came to the right place, and I know that our panelists are going to be very keen to have this insight as they present their portion. Right now, I want to introduce our sponsor, Glenn Gibbons, who's the editor and publisher, I'm sure most of you know, from Inside GNSS, to officially welcome you and tell you what he hopes you'll get out of today and why today is important. So, Glenn, welcome from Oregon to the webinar.
Thanks, Mike. And welcome to all of you to Inside GNSS Magazine's web seminar on hybrid positioning and technologies for mobile users. As Mike mentioned, we have more than 850 GNSS professionals from around the world registered for today's seminar, and we are delighted to have you with us online. Now, first, let me just say a bit about our sponsor, Spirent Communications. Spirent is a leading developer of test equipment for system integrators and product and application designers working in the field of positioning and navigation. Many of us know Spirent is a provider of GPS simulators and more recently multi-GNSS simulators. But Spirent also has systems that enable engineers to set up test environments for assisted GPS and even assisted GNSS techniques. And now Spirent has developed and fielded systems to support hybrid navigation and positioning tests. These tests emulate cellular network and Wi-Fi positioning elements as well as GNSS. Like Spirent, we at Inside GNSS have been paying close attention to the growing interest in hybrid positioning. You know, as a journalist, I've been covering this field for more than 20 years. It seems pretty clear to me that GPS, and by extension the other GNSS systems, represent the most significant positioning, navigation, and timing technology ever invented. GPS has literally put accurate real-time location into the hands of citizens around the world. And of course, it doesn't hurt that it's free either. But as amazing as GPS is, it has its weaknesses and vulnerabilities. And as we all know, GPS depends upon signals transmitted from distant space that arrive at Earth with such low power that they disappear into the noise of the RF spectrum. You all have probably had the experience of using equipment that cannot pick up GPS signals in some places, especially inside buildings or in urban canyons where the satellite signals are blocked or reflected. Now, in the past, that might not have been made very much difference, but with other developments in mobile technology, such as the widespread use of cell phones and portable computers, consumers have come to expect quick and accurate location information wherever they go. So today we're going to hear from 4 experts about some of the leading candidates among the technologies that can be used with GPS to ensure ubiquitous positioning and navigation capability. These technologies include the use of multiple GNSS systems, Wi-Fi, cellular networks, and inertial positioning. Over the next hour and a half, we will learn more about how these technologies can work together to provide accurate, robust, and continuous positioning, as well as some of the best practices for incorporating these technologies into the design of products and systems. So on behalf of Spirent and Inside GNSS, I thank you for joining this webinar and hope that you find it informative and useful. So let's get started. Mike, it's back to you.
Thank you so much, Glenn. And you know, it's interesting, folks. I welcomed everybody from around the world, but our panelists are from around the world too. And to start is Tony Haddrell from the UK. And Tony's topic is going to be the ultimate location technology, GNSS. In case you're not familiar with Tony, he's been in the radio location industry for about 30 years, and for more than 20 of those, he's been associated with the GPS system, and he's also recently with GLONASS and Galileo. And after graduating in physics from Imperial College in London, Tony joined the Decca Navigator company, later to become part of Raycal. And he's also worked at Marconi, Navstar Systems, and as well as others. He's filled roles in engineering, senior management, marketing, all closely associated with the positioning and timing industries. He founded Pinpoint Positioning to further explore the use of GPS and Galileo receivers that can work indoors. Tony, absolutely delighted to have you from the UK, and welcome to the webinar.
Thanks, Mike. And today I get to talk about the use of satellite positioning in harsh signal environments, such as urban canyons and indoors. The question we're trying to answer is whether GNSS on its own can always provide the user with his location in a reasonable time and to good accuracy. So the challenge we face is that although GNSS signals were originally designed to provide good location accuracy and autonomous operation in line of sight situations, that is with a clear view of the sky, this is not what our mobile users expect. In fact, our users don't actually care and often don't know how their position is determined, and probably neither should they, but they do expect to be able to get a fix wherever the host device works. So in other words, they see location as a utility that always works and not as a premium service that will only work in some situations. Anyway, this has resulted in GNSS receiver designers coming up with high sensitivity receivers so we can cope with less signal, and finding ways around some of the traditional limitations by using the network resources, and that's on things like assisted GPS over cellular networks. But however good the receiver designers can make the sensitivity and acquisition of signals, and we are getting close to the physical limits there, the user will always be able to find some location like a basement parking lot where there is simply no signal. Okay, let's have a look at a typical environment. This is an urban canyon where the surrounding scenery prevents the signal getting from the satellite to the receiver. And looking at the picture, although there's still outdoors here, we can only see a small patch of sky, and there may or may not be a satellite visible in that patch. But because the signals easily reflect from planar surfaces, just like light does, so shiny materials are really good for reflecting things, our receiver captures any number of reflections from all these buildings you see around there. And these are tracked by the receiver, but the path length to the satellite is now longer than the direct one, and therefore it messes up the measurements of the time of arrival of the signals at the receiver. There's another limitation too. Our high sensitivity receivers impose long integration times in the signal processing up to a couple of seconds, which in turn limits the user dynamics that the receiver can cope with, and tends to blur together all these received reflections, and in some environments we can see up to maybe 5 reflections from a single satellite. So we can see that reflected signals are useful in finding some measurements when we're short of direct signals, but these measurements may be flawed and lead to poor accuracy of fixes. So with the advent of new GNSS systems, we could eventually see up to about 30 satellites in the sky at any one time. What are the chances of improving the number of satellites in that patch of sky? Well, right now we have the GLONASS system available to add to GPS, and we can use that to see how things improve. What we find is that availability gets better, and by that I mean places where we had limited or no fixes now get improved coverage, but what we don't see is much of an improvement in accuracy, so we're still relying on bounced signals and therefore flawed measurements. And also it requires more battery power and more computing power to use both systems, but it does move us in the right direction. The benefits, I think, are good enough for phone manufacturers to want the addition of GLONASS, and so watch out for GLONASS-enabled phones hitting the marketplace next year. Okay, now we're going to take a look inside the correlator, the heart of the GNSS receiver. And what we're looking for, or what the receiver is looking for, is a nice correlation peak formed by matching the local code replica and the incoming signal. And if we look at the diagram on the top right there, the left-hand peak is pretty much what we expect to see. It's a peak that's plus or minus 1 chip wide. Each of those vertical bars is a quarter chip. And we measure the top of the peak as the time of arrival of the signal. Now what we see in that particular diagram is a second peak, which is a reflection that's coming into the receiver. And that is quite a long way behind. It's about 300 meters of extra travel there, so that's come quite a long way. And usually we don't see reflections that are that far behind. So my main picture here is a sort of time travel through all these correlator peaks that we see, and it's taken with a static receiver in an urban canyon, and time runs from the front to the back, and there's about 15 minutes of static signal there, all for one satellite. If I look at the middle diagram on the right, I see that the two signals that I had at the top have now merged together, and they sort of drag the peak off to the right, and you can see there that the measurement we get would be not huge, but maybe 20 or 30 meters late. If I move down to the bottom diagram on the right-hand side, something quite strange has happened. The amplitude's got higher. We've added together a number of reflections in various phases, and we've actually managed to make the peak of that resulting graph early. So now we're making a measurement that appears that the user is closer to the satellite than he really should be. And this one at the bottom looks kind of perfect to the receiver because it is still about the right width, and so the receiver is unable to sort that out from a really good straight signal. In most cases, a receiver in a heavy multipath environment is burning more processor power trying to mitigate the bad measurements than it is tracking the signals. Okay, we're looking now at vehicle navigation and the challenges we have with that. Just a quick word about the photo. This is somewhere in Taipei, and the photo is taken from the sidewalk. The road is to our left and is underneath that elevated railway that you see there. And we get a lot of reflections, virtually no direct signals, and we only see direct signals at intersections. So we use a different technique here in order to keep the position fix on the road. We rely heavily on the motion vector, since the Doppler measurements are usually less effective by multipath. And we can tell that we're driving from the measured dynamics, and so performance is often quite reasonable while the vehicle's moving. However, when the vehicle stops, we get a zero length vector, which means it's of indeterminate direction. And that may cause other bits of software, such as map matching software, to flip to another road because it thinks we're at 90 degrees to our original travel. And once we stopped, of course, we can no longer be sure that the user is still driving. And it gets even worse. There are more difficult environments. This is a shopping mall, 3 floors, and a mixture of open and closed-in areas. This time we can't get much help from the vector. The shoppers can, of course, go in any direction. They don't have to stick to the streets. There are usually no maps of these places, so there's no help to be had from map matching or indeed measuring the dynamics. Multipath, though, is often better, at least giving some lower path length errors, and sometimes we get enough direct signals heavily attenuated to get a fix from direct measurements. However, because of the low signal environment, these are still in the sort of 20 to 30 meter range. There are often a few special cases too. Elevators are kind of weird. They return the position of the top of the elevator shaft for reasons I won't go into, but there are all kinds of things that we need to mitigate when we're indoors in these kind of locations. And of course the users expect us to determine which floor they're on, for which GNSS is just not accurate enough. So does GNSS need help? Well, user experience everything, and we rely on our many millions of users now to keep us in business. So anything that can help with location accuracy has got to be a benefit. And we should remember that a GNSS receiver working hard is not particularly power efficient either. Many host devices, mobile phones especially, already have a raft of technologies that can help. And for instance, using the accelerometers just to know that you haven't moved is a big help, because why should we do a new fix if we know the last one is where we still are? And things like Wi-Fi, gyro, altimeters, compasses are also on offer, so we should try to make the most of their location capabilities, and we're going to hear more about that later. So my conclusion is that the user will always expect more, and that location from GNSS on its own is not enough.
Tony, thank you so much. That was great. And we're going to have you back in just a moment after we have Farshid up, and then we're going to take some questions from the audience. So thank you so much. Now we're going to hear the next topic, which is hybrid localization, Wi-Fi plus GPS. And our distinguished presenter is Farshid Alazad Shabiz. And he's the chief scientist at Skyhook Wireless, where he's responsible for R&D of their positioning technology. He's got more than 17 years of industrial experience in the design and implementation of satellite and wireless networks. And before he joined Skyhook, he was the lead or the head of the communications section of Advanced Solutions Group, part of the cross-country automotive services. And earlier he worked at Hughes Network Systems. He was also part of the design and implementation team of the first satellite-based mobile network, ICO, Global Medium Orbit Satellite Network Voice and Data Services, and Thuraya Geosatellite Network, and the first phase of the MSRAT High-Speed Data Network. He's also on the faculty of Boston University. He received his PhD from George Washington University and his MS from Tehran University. Farshid, we're delighted to have you, and welcome to the webinar, and I'll now give you control of the mouse and keyboard.
Thanks, Mike. So what's Wi-Fi positioning? Why Wi-Fi positioning is important? What's the impact of this technology, current status, and its future? Let me start with this slide, which is very interesting statistics, maybe the reason that we have this webinar. One of the main reasons of so much attention to positioning technology recently. This shows growth of location applications in last couple of years, going from 50 to 60 applications to more than 10,000 applications now. So message here is really location is becoming an attribute of so many different kinds of information. And the next slide, dividing these applications into categories. Since introduction of GPS, main focus was on navigation. And now, in the last couple of years, we see a very diverse use of this technology. Although navigation is still important, it's only 20 to 25% of use cases. So let's go to Wi-Fi positioning. So metro-wide Wi-Fi positioning system. It started with standard itself. 802.11 standard was published in 1997. 802.11b standard was published in 1999. Since early years, idea of using wireless LAN access point as anchor points to position users existed. A lot of research labs, MIT, University of Washington, Seattle, University of San Diego, Intel Research Lab, Microsoft Research Lab, all investigated this. And in 2003, Ted Morgan and Mike Sheen started Skyhook and introduced first commercial metro-wide Wi-Fi positioning systems. The next important milestone, in my opinion, is when Wi-Fi positioning was pushed to mainstream by Steve Jobs by announcing deployment of Skyhook Wi-Fi positioning on iPhone and iPod touches, and later many more Apple devices. And I encourage you to take a look at Macworld Keynote 2008 when Steve Jobs talks about Wi-Fi positioning. And now Wi-Fi positioning is becoming really part of positioning solution of almost all the players in this domain. And the main reason, in my opinion, and I believe it's because of its accuracy, median error of 20 to 40 meters, and time to first fix below 1 second. And also the impact on power, as Tony mentioned, other technologies, satellite-based, when they are in a challenging situation, they spend a lot of power to get a fix. And having this augmented technology can help return location quickly and save power. So let's go to the Wi-Fi positioning. So metro-wide Wi-Fi positioning relies on all existing access points in the wild, all the public and private access points, the ones that are in our offices and in our houses and everywhere. These are two pictures from Chicago and Manhattan showing penetration of these Wi-Fi access points everywhere. And wireless LAN access points, they announce their presence by broadcasting beacons with their unique MAC addresses. So each and every Wi-Fi access point has a unique MAC address, and it broadcasts its presence and this unique MAC address periodically. And Skyhook started driving all streets of United States, Canada, Europe, Southeast Asia, with a couple of hundred cars, and detected these AP, these access point beacons, and triangulated these access points based on received signal strength. Now we have 250 million wireless LAN access points in the Skyhook database. And also there's one very important thing that I want to mention, that Skyhook also characterized radio coverage of each and every access point based on its understanding of its coverage at the time of sampling. Now, when application requests its location, mobile device detects wireless LAN access points with their unique MAC addresses and uses wireless LAN access point database and its data to calculate exact location of the device and return that location back to the application. So again, the sequence is we have a database of all access points with their data, location, and their characteristics. Application requests the location. Mobile device detects access points with their unique MAC addresses, uses access point data and calculates exact location and passes that back to the application. So behind this neat and new idea, there are some complexities because Wi-Fi access points are not really calibrated for position. And more importantly, they move. This is a very dynamic environment. And also some of them are mobile. They are on the cars and buses. So this actually is different than what we have in GPS and cell positions because our anchor points now are moving themselves. So therefore the approach in Wi-Fi positioning is statistical. It's a stochastic system and not like GPS and cell, which are deterministic systems. And I want to point out to the last bullet here in this presentation, in this slide, which says continuous feedback system. So this is the very first time, since it's a stochastic system, it uses usage as a feedback to actually have a self-healing capability integrated into the system, because each and every use is a snapshot of access points at a time and at that location. So one example, if user actually detects 3 access points, 2 in Boston and 1 in Chicago, what would be the return location? So return location is based on all the observation up to the time of this user detection of 3 APs. All those statistics up to the time of detecting these 3 APs by this user can be used to return location, to actually solve this contradiction between 2 access points in Boston and 1 AP in Chicago. For example, if that 1 AP in Chicago was confirmed in Chicago yesterday, then location is Chicago. And I don't want to go to the details, but this is what I mean by having a stochastic system versus deterministic system. I want to go to some interesting, fun statistics. So Wi-Fi positioning now, the Skyhook technology deployed on over 100 million devices. We received 400 million location requests on our server per day, and we have 250 million access points in the database. This is very interesting picture. I wanted to actually show you that from this 400 million requests that we receive at Skyhook server, they are from everywhere and not only urban Canyon. This is a picture of 1/3 of the state of Massachusetts. And on the right corner, we have basically Wi-Fi positioning usage. Each square is a 50 request. So it shows actually that Wi-Fi positioning usage is very much everywhere. And I contribute this to the fact that Wi-Fi positioning is returning location within a second. And some performance numbers. So this is the WPS Wi-Fi positioning performance. This is the test which was done in Manhattan, Chicago, and San Francisco. As you see, it's a very challenging environment for GPS. And availability of Wi-Fi positioning system in those areas is almost 98%. We detect average of 10 access points in those places. And the accuracy, as you see here, in this test is in order of like 15 to 20 meters. The next test is, again, Wi-Fi positioning system test for indoor-outdoor. This was done in Back Bay in California, in Bay Area in California. And again, the accuracy, I wanted to just show some accuracy numbers from real world and also the availability that we see in Bay Area and California in this case. The next slide is a sample of test drive. This is Wi-Fi positioning in tracking mode. This is downtown San Francisco. 2 examples. On the right-hand side, we see definitely a challenging environment for GPS, and on the left-hand side, we see Wi-Fi positioning only in tracking mode. And last one, we have current technology taking GPS, Wi-Fi positioning, and cell positioning outputs and and basically return the best location in time. Future, in my opinion, is in tight integration of GPS and Wi-Fi positioning systems. When I say tight integration, I really mean at the raw measurements level, and this is a product of the Skyhook results. What we did, these are selected points in the places that GPS couldn't return location, but GPS acquired at least 2 satellites. And with this slide I wanted to show, Wi-Fi positioning systems can take advantage of even 2 satellites measurement and have like 15% improvement. And we use Surface Star 3 in this case. So I'm going to conclude my presentation with the fact that Wi-Fi positioning systems is really in the core, and it supports 10,000 applications. Wi-Fi positioning is a stochastic system. That's one of the main messages. And also the fact that there's a lot of potentials in integrating Wi-Fi positioning systems and a GPS to have a universal coverage, reduce time to first fix, and also reduce power consumption. Mike, back to you.
Farshid, thank you. That was terrific. And we're going to call you. I'd like you to stay there. I'm going to call Tony back in just a second. But now we want to go to our second poll. And I'm going to launch it right now. And if you would tell us, how long do you think it will take before the level of accuracy that indoor consumer apps require will be practically available? And let's share the results. Pretty interesting. So, 38% of you think 1 to 3 years. 44% say 4 to 5 years. 11% 6 to 7 years. 4% 8 to 10 years. And 3% more than 10 years. So, excellent. And let me now call back Tony and Farshid, who's still there, and let's start with a few questions. But before I do, any comments on the poll results that we just got? For Tony, do you want to take that? Any comments?
Yeah, I think that's interesting. The good news is that those of us on the panel have still got careers for a few years yet, by the look of it. And I think we pretty much agree. Farshid, you agree?
I do agree, and it's very encouraging that people actually see this problem can be addressed not in a very long time. I hope 1 to 3 years.
Well, terrific. Here's a question that came in for you, Farshid. Where do you see pseudo lights fitting into this ecosystem?
Let me actually quickly first explain what the pseudo light is. The idea is using same GPS transmitters inside buildings and on the side of the buildings. And the idea, the basic idea is using our GPS receivers embedded in our phones and in our devices and not have a new radio. It's a very interesting idea. And in my opinion, the main problem of pseudo lights is near-far problem, causing interference and also installation. Any solution which needs a new infrastructure and it wants to solve metro-wide problem, is going to face this installation problem with power, locating these devices, troubleshooting those devices. So I think pseudo lights can be part of the solution in a very limited aspect, in a very limited way.
Well, thank you. Tony, here's a question from Ken. How can Multipath make the receiver appear closer?
Okay, this is a trick of amplitude and phase. If you consider a correlation peak like I showed you in the slides, and you add to it a second one that overlaps, let's make it the same amplitude just for fun, but it's upside down because it's 180 degrees out of phase, and that just happens to be the distances involved. And you add those two together, you get a new smaller peak that's actually in advance of the original one that you started with. So yes, it can make it look earlier.
Great. Farshid, here's a question. I hope I pronounce it right. Phoenix. People move, and their Wi-Fi stations move with them. How do you use Wi-Fi to always get a reliable fix?
So as I mentioned, this is one of the challenging problems. Wi-Fi positioning environment itself is a very dynamic environment. So in our system, we rely on statistics that we collect from that access point from day one until now and try to actually identify those APs. Very simple example is if I see 10 access points and 9 of them are actually telling me that I'm in Boston and 1 of them is telling me in Chicago, I'm almost sure that one AP moved from Chicago to Boston. It's going to be much harder when I have 1 AP in Chicago and 1 AP in Boston, 1 AP in Chicago, or 2 AP in Boston. Then it needs a little bit more elaboration. But definitely it can be detected looking at the statistics of observations over time.
Great. Tony, here's one for you. This is from Hugh. Are these graphs, or the graphs that you were showing, taken from real-world data, or are they simulations?
They are real-world data. We have, I think, never really managed to simulate multipath sufficiently well to match urban canyons. What we do these days is actually go and record the signal in a particular canyon or indoors or wherever, and our good friends at Spirent can fix you up with some kit to do that.
Terrific. And I just have another one here, as long as you're on, Tony. This is from Olaf. To receive the multipath signals better, can a rake receiver be used for GPS?
Yes. There's a lot of expertise out there on getting rid of multipath, especially in the sort of surveying type industry, and all kinds of narrow correlation rake receivers. They don't fit into mobile devices very well. First of all, we like to use very narrow bandwidths because of all the interference in the devices, and these guys are typically all wideband. And secondly, they rely on being able to find the direct signal, and of course, as we saw in the environments, we quite often don't have the direct signal at all. So it is a bit of a challenge, and we do know those technologies are out there. They don't fit very well with the mobile platforms.
Great. We're going to take a couple more before we move to the second portion with Brock and Nasser. But Farshid, here's one from you. This is from Logan. Let me read it. In many applications, it is important to know what floor you are on. For example, shopping, geofencing, indoor navigation. So how does your system address this issue? And that's actually, Tony, if you have a comment on that to jump into. But go ahead, Farshid, and take that one.
So technology itself doesn't have any limitation. None of the Wi-Fi positioning systems as of now return altitude. None of them return height. But there's no really limitation in the technology itself. But problem is when we return, let's say, height or altitude of 100 meters, translating that 100 meters to second floor or fourth floor or first floor is a question. In other words, we are not interested to know that we are 100 meters above sea level. We are more interested to know which floor we are in. But as I said, there are solutions to this, but I think maybe because of lack of need, maybe most of the applications didn't need it, or maybe some challenges on collecting this kind of data. Nobody really tackled this, but as I said, this is a problem which can be solved.
Great. Farshid, let me give you this, and we've got lots of questions coming in, so I'm going to take this, and then we're going to move to the second part. This is from Prasanna, and what happens when the APs are mobile, like in MiFi's?
Same thing as first question or other question regarding regarding APs which move. Mobile APs can be detected, and we do detect them in our system. And the way that it's done is based on their behavior. So mobile APs, looking at, again, to my very high level explanation of this system, statistically they're going to behave in a way different than non-mobile ones, and we can identify them. Definitely, if mobile AP comes to life very first time, cannot be detected. We cannot detect it very first time, but as it goes to as it moves around and we have more samples, we can identify them and detect them. And we, in our system, we remove many MiFi and other mobile APs. The APs on the buses, and then those kind of APs.
Great. Thank you, Farshid and Tony, and that was terrific. We've got lots more questions for you. I'm now going to bring up our next presenter, who is Brock Butler, who's the Director of Wireless Location Technology at our sponsor, Spirent, and his topic is going to be on cellular network positioning for mobile devices. And a little bit of information on Brock before I bring him in. He is, as I said, the Director of Wireless Location Technology. He joined Spirent in 1999, and he spent about 12 plus years working in the wireless communications field, and he focuses now on the marketing of location technology test solutions for mobile devices. He also has an MBA in management and international business from Rutgers, the State University of New Jersey, New Brunswick, and a BSEE in computer engineering from Villanova. Brock, welcome as our other global presenter from Canada to today's webinar. I'm now going to turn the keyboard and mouse over to you.
Okay, thank you, Mike. So my goal here is to provide a brief overview on cellular network positioning for mobile devices. And there's a lot of technologies that fall under that umbrella, so I'm going to try and give an overview of the major technologies as well as implementation options for implementing them. But to start with, let's make sure we're all clear on what I mean when I say cellular network positioning. What's the definition? So what I mean is any positioning technique that uses one of the existing cellular network technologies out there to allow devices to compute position. So using those ugly base stations that you see around like CDMA networks, GSM networks, LTE networks, WCDMA networks, these types of things. To contrast it, there's things like AGPS where you provide assistance data to devices over the cellular network. But what I'm talking about here is technologies that use exclusively the cellular network technology. Very briefly here, this type of technology works for any device with a cellular modem. Of course, that includes mobile phones, but increasingly there's a lot more devices like tablets, laptops, connected PNDs that also have cellular modems. So this can apply to a lot of devices. So let's just talk briefly, where does this fit into hybrid positioning and why do we need it? I would say cellular positioning is both a complementary technology to the others, and it can also be used as a standalone technology in some cases. You may be familiar with something like this here, where you try to get your position and you quickly can find that you're in a very big circle like this. That would be the cellular network position, and then maybe you get a smaller circle like this. Maybe now you're able to use something like Wi-Fi. Or maybe you eventually get to a dot like this, which would be something like GPS or GNSS. So the reason cellular networking can be useful here, for one, it covers a majority of populated areas. It covers more areas than Wi-Fi. It's also built into so many phones, and I must say most phones on the market, mostly in developing countries, don't have GPS. Many of them don't have Wi-Fi. So in many ways, cellular can be the least common denominator as far as positioning goes. It can give you a way to get position even for very low-end devices which only have a cellular modem. It can work indoors. It's very fast, which is why it can be complementary, because it can get you a course position very quickly. And really the only downside is the accuracy is not as good as the other methods that we're discussing here today. So let's cover the technologies here briefly. I've broken it down into a few different groups. Let's start with cell ID-based positioning. What you see there is a base station with 3 sectors. The red push pin is your location, and The way this technology works, it's very simple. You know the location of the base station, you know the location of the sector, and if you can return the sector ID that you're in, you can attach a position to that. It's a very coarse position, it's the entire sector, but it's better than nothing. And you can have both, the UE is making the measurements in all cases, but the actual position can be computed either on the network side, if the UE is returning the sector ID, or it could be computed at the mobile side if there's a local database. To take that a little bit further, there's something called enhanced cell ID, where you can get a little bit more accurate location. It still uses the sector ID, but you can combine that with a timing advanced measurement from the serving cell and some timing offset measurements from neighbor cells, which will allow you to, within the sector, know more precisely where you're located. So this will return better accuracy. And it's also based on device measurements, but the position is generally calculated from a network entity. Now, moving on to the next section, there's a bunch of acronyms here, but they all work pretty much the same way. It's called hyperbolic time difference of arrival, or sometimes called multilateration methods. In each of these cases, the device is making measurements of time difference of arrival from the different base station signals. So here's a picture with 3 base stations. The phone's making a measurement of the timing offset, the time difference of arrival, and it can trilaterate its position based on that, knowing where those base stations are located. So AFLT is an advanced forward link trilateration common in CDMA networks. OTDOA, or observed time difference of arrival, is something that's going to be rolling out in LT networks. And there's also something called EOTD, which is available in WCDMA networks. So there's a bunch of ways to do this, but they all pretty much work the same way. And that's from device making measurements and typically a network entity making the position calculation. The inverse of this is UTDOA, or uplink time difference of arrival. In this case, the base stations are making measurements of the timing offset and of course making a computation of location. So this is a purely network-based approach using the same principles. And then there's a few other methods that are worth noting. One is angle of arrival. Base stations typically have multiple antennas for things like receive diversity, and you can actually compute the angle of arrival of signals based on when each antenna receives a signal. That can be used to locate phones. That's commonly called triangulation, and it's a purely network-based technique for positioning. And finally, to round out the list here, there's something called cellular signal fingerprinting, or sometimes called RF pattern matching. In this case, it works on the principle that every location has a unique RF signature. The multipath environment, the different cells that you're seeing, the phone makes a measurement of the environment, and then it's compared against some database of fingerprints or signatures from around the world, and statistically can match what location you're in. So this is an emerging technique that you might be hearing about. Okay, and this just gives you an overview of some of the performance of each technique. I think Farshid also gave some metrics for Wi-Fi that could be compared against this. Generally, the accuracy is not as good, but generally the time to first fix is fast, and the hyperbolic TDOA methods generally are the most accurate, although cellular signal fingerprinting, I've certainly seen some indications that can be quite accurate as well. And now I just want to cover a couple examples just to show you how this is used in the real world. So here's one for E911 location in North America. Cellular positioning is commonly used as a fallback mechanism. So this is one way that cellular can be used as a fallback. In the cases where GNSS is not available, you can fall back to, I guess the best one would be AFLT on a CDMA network. So if your network supports that, that would be the best way, or in future LT networks, OTDOA will be a common one. Or if those aren't supported, cell ID or eCell ID can be a good fallback position. These are actually needed to meet some of the E911 device requirements of 50 meters 67% of the time and 150 meters 95% of the time. Since GNSS is not available everywhere, these are great fallback mechanisms. They are used in North American carrier deployments. Taking that a step further, I mentioned on the previous slide that AFLT would require at least 3 base stations. So in the case where you only have, say, 2 base stations or 1 base station, but you also can't see enough satellites, it is possible to combine GPS and base station measurements to do a true hybrid position fix. To do this particular one, you would need a synchronized network such as CDMA, although it's also an option on LTE to have a synchronized network. But the phone's actually making measurements of base station offsets and satellite offsets. Because the technologies are very similar, it can use a combined input of those signals, and it can compute a position based on that. So that's something that is supported in CDMA networks today. And then just to talk a little more about implementation options. This is something maybe we can go over more in the Q&A, but there are a lot of different implementation options. Many of them are proprietary, but there are some standardized approaches as well. Enhanced Cell ID is now standardized as part of 3GPP Release 9, which applies to LTE. AFLT has always been standardized in 3GPP2 for CDMA devices, and OTDOA is standardized in Release 9 for LTE, and UTDOA in Release 10 for LTE. So those are some standardized approaches. And I guess my view on this is that there's probably always going to be room for both proprietary and standardized approaches, but I think the standardized approaches will become more popular as carriers adopt them. And so that's one of the areas that Byron is focused on. And also all these methods require UEs to make accurate measurements of these signals. So of course, UE device testing is important to make sure that they can make the measurements well. But we can get more into that in the Q&A if there's additional questions on that. I'll just leave you with this. As I said before, I think cellular positioning is both a good complementary technique and good on its own. All mobile phones have cellular. They don't all have GNSS or Wi-Fi. And in the cases where they do have GNSS, Wi-Fi, or sensors, it's a good complementary technique to be used, and I think it should be part of any hybrid strategy addressing mobile devices. So thank you. Back to you, Mike.
We're going to have you back in just a moment. And now we are going to officially welcome Nasser El-Shami. His topic is trusted positioning. And let me give you a little background. He's a professor and former head of the Department of Geomatics Engineering, and he's a leader of the Mobile Multi-Sensor Research Group at the University of Calgary in Alberta, Canada. He holds a Canada Research Chair in Mobile Multi-Sensor Geomatic Systems, and his area of expertise is in the integration of GPS, INS imaging sensors for mapping and GIS applications, with special emphasis on the use of multi-sensors and mobile mapping systems. Recently, in 2009, he started Trusted Positioning with two former group members, and Trusted Position Incorp, or TPI, integrates MEM sensors with wireless technology such as GNSS to provide seamless, low-cost, and accurate navigation in areas where wireless signals are blocked or inaccurate. They service three primary verticals: mobile handset, location, automotive, and machine control. And his presentation will focus on more of the mobile handsets, such as pedestrian and vehicular applications. Nasser, how are you doing today?
Excellent. Thank you very much, Mike, for the introduction.
It's all yours. It's all yours.
Excellent. Thank you. So the focus of my presentation, as Mike indicated, will be on sensors, and more specifically MEM sensors, and their promise to the pedestrian and vehicular location and navigation applications. So I would like to start first with a very brief introduction to inertial navigation. Inertial navigation is simply an integration technology. It consists of a detector and an integrator. It first detects the acceleration of the user through accelerometer sensors, and then by integrating this acceleration 2 times, we end up with velocity and then with position. Gyroscopes are typically used to transform the distance or the travel distance into a navigation frame of reference to produce location, examples such as latitude and longitude. The major advantages of inertial navigation is simply the system provides all the information needed for location. It also produces velocity, which is needed for navigation. It also produces attitude or orientation, which is very important for many of nowadays, consumer applications such as location-based gaming. So the previous 3 presenters focused mainly on RF technology. I believe that there is no question that the current location technologies for navigation primarily rely on wireless signals such as GPS. However, RF technologies suffer from shadowing, reflection, specifically in urban environment and indoor, and therefore they might fail to meet the reliability and availability requirement by many location-based and indoor navigation applications. There is also technologies that are portable, such as RFIDs, but the infrastructure to deploy and maintain them is cost prohibitive. Of course, Wi-Fi is a similar technology that requires significant maintenance to provide accurate and available location. You have inertial technology on the other hand, that have also issues of portability and affordability. Specifically, meaning that for large inertial systems, although they are accurate and they overcome the availability issues of wireless signals, but they are expensive and bulky. Of course, we have seen in the last few years the next generations of inertial systems, which is the micro machine sensors. They are very portable and affordable, but they suffer from very large drift errors if not dealt with properly. So the question right now is if there is a winner from all these technologies, and I believe that the clear answer is no. So the results of that is that there is no clear winner in technologies for location-based services, and also there is inability to capture the emerging low-cost markets such as gaming and social networking. So given these facts, what can inertial sensor do to help achieve reliability, accuracy, and cost effectiveness that is needed again for many consumer, indoor, and urban areas applications? I want you to imagine with me the next generation enabled portable device. That is not only your phone, not only your calendar, not only your book, but also your trusted positioning device that is accurate, always available, and is easily portable across consumer platforms, including walking and driving. Having such a device, of course, will enable many new applications and open many new markets, such as social networking, advertising and security, and of course, augmented reality and location-based gaming. So the question is if this is possible, and if it is possible now? And if it is possible now, can the same device used for both pedestrian and vehicular location applications? I firmly believe that this is possible, but possible only through smart sensor and data fusion algorithms, even without the need for additional infrastructure. In fact, they require sensors such as magnetometers, gyros, accelerometers, and barometers, and wireless signals are already in many of everyday platforms such as cars, smartphones, and PDAs. These sensors, when integrated the right way, will unleash the true potential of sensors and will provide an uninterrupted and accurate positioning using low-cost sensors. So the question is, given that these sensors are available almost everywhere, why haven't they been used in mainstream navigation applications? And I think there is few reasons. I'm only going to share with you 3 of them. The first reason is due to usability. The user is typically looking for constraint-free navigation with the ability to operate their mobile devices in any orientation with respect to their body or with respect to the vehicle while traveling. This, of course, requires that the fusion algorithm of this sensor to continually correct for the misalignment between the moving platform, be it a person or a vehicle, and the mobile frame, so that the device can be used without any constraint of being fixed to the user belt or dash mounted in a vehicle. The second reason is also related to usability. As current solutions using sensors for navigation are application specific, and typically they use different algorithms for walking and driving. For sensor technology to be accepted by consumers, the sensor fusion algorithm should allow a user to operate their mobile device when walking, driving, or any other moving platforms while navigating. This will only happen by autonomously detecting the mode of motion and by setting the proper sensor fusion algorithm, which is suitable for the detected mode of motion. Furthermore, when driving, the algorithm should have the capability to accept any available aiding information. For example, in vehicle navigation, the vehicle sensor information can be obtained, such as speed signals from the vehicle to improve the navigation results. The third reason is mainly was related to the sensor, and MEMS in particular are their errors, which lead to quickly accumulating location errors. These sensors which are typically not modeled, or these errors, if it's not typically modeled properly in the traditional navigation information, will lead to large position drift with respect to time when navigating these sensors in standalone mode. This requires the fusion algorithm to implement advanced sensor error modeling in order to allow navigation without the need for wireless update for a long time. So the next set of slides, I will try to demonstrate the potential of low-cost sensors when the above-mentioned problems are resolved. I would like to demonstrate that through a number of scenarios. The first scenario will be for a pedestrian walking indoor inside a building without wireless signal, and then how Wi-Fi can help in improving the sensor solution. The second will be for car navigation using mobile devices, and I'm going to demonstrate that with driving in downtown San Francisco, which is one of the most difficult environment for wireless signal. And thirdly, I will show that using what we call strap-down or in-dash car navigation. And for all these tests, we're using consumer and phone-grade inertial sensors, and typically we either have a reference system, which is a very high-end system, or we have a map to compare to. So the first test, as I mentioned, will be positioning inside buildings. This test was conducted in Taipei in a 13th-floor hotel. It's a walking test for about 15 minutes with about 8 minutes indoor, including a few stops in an elevator while traveling up to the 13th floor and down to the ground floor. The right-hand image here shows 3 different trajectories. The first is the green line, which shows the reference trajectory, which was hand-drawn in a Google Earth image. The blue dots show GPS solution only, while the red shows the sensor fusion when integrated with GPS. And more specifically, in this test, 3 accelerometers, 3 gyroscopes, 3 mags, and 1 parameters were integrated with a U-Blox LEA 5T GPS receiver. The sensor in general, as I mentioned, were all low cost, costing less than $10 in quantity. In this test, the unit was handheld in front of the user to emulate a texting or navigating scenarios. As we can see from the blue trajectory, that GPS actually has several fixes inside the building, right? But this is mainly due to a glass roof, but in general was largely unavailable and inaccurate inside the building. Even outdoor, there was many sections that the signal were blocked by low, tall buildings that affected the GPS accuracy. So I want to zoom a little bit into the left figure, which shows actually the details of the sensor solution, which, as you can see from this left figure, that all turns and the shape of the trajectory is very clear. So this figure shows a zoom of the trajectory where the user actually went inside the hotel from the back door, and then went through a couple of rounds, and then take the elevator to the 13th floor, walk again in the 13th floor, takes the elevator down and then exits the building again. Very clearly here that we have definitely errors that have accumulated. Again, this is only based on sensor technology, and the errors were about 18 meters. We're not counting for any other aiding or other sources. What's also important here that all trajectories available, which means that we have 100% availability, but it's more important that the sensor also will provide what we call the elevation or the vertical profile of the user. And this is shown here in the next slide. So in this slide you have two pictures. The left picture shows actually inside the hotel and shows the elevator and shows also the glass roof. The right plot showed the trajectory, the vertical trajectory, which has been obtained or derived from a barometer, which mainly retained the absolute height, while inertial sensors help smooth the noise of the barometer. The outdoor GPS was actually used to correct the barometer for its large turn-on bias. You can see actually in some areas here, GPS has been able to fix for a few measurements, but however, in most of the cases it was not there, and also the accuracy of the height was not correct. So the second set of tests is related to GPS and Wi-Fi. In this case, this is again for walking indoor. The following figure shows GPS and Wi-Fi fixes for a person moving outside and then inside a building with Wi-Fi. The orange points are GPS position fixes from a Star3 GPS receiver, while the yellow dots are the derived Wi-Fi fixes using path loss modeling from line of sight access points inside the building. It is clear from these figures that we cannot clearly define the trajectory of the user. By integrating MEMS sensors, and more specifically again 3 accels, 3 gyro, and 3 mags and 1 barometer with the GPS and Wi-Fi fixes on Wi-Fi, the trajectory of the user is very clear. In fact, the user walks outside the building, went inside, and then walked up to 2 floors, and then made a big loop and went inside the second floor hallway. The trajectory is 100% available, and in most of the cases, the accuracy was about 10 meters of the entire test, which is about 10 minutes. The green actually solution here is a trusted positioning backward smooth solution that was used actually as a reference for this test. The third test is for driving downtown using a mobile handset, where in this test actually the mobile unit was on the belt of the user for part of the test, and then the unit was set on the seat of the vehicle while navigating the rest of the test in downtown San Francisco. What makes this test difficult for the sensor solution is that the device is not firmly tethered to the vehicle, and therefore it will experience jitter, shake, and rotation. The unit was also communicating wirelessly to the vehicle OBD2 to obtain the vehicle speed. Here are a few pictures of the downtown San Francisco. The test also experienced a number of tunnels and of course a number of steep hills, which again one of the most difficult sections of most difficult situations for GPS. So the next slide I will share with you some of the results. Again, due to time I only can share one. This shows actually the GPS, the blue dots show the GPS solution. In most of the cases, of course, the GPS solution was available, but in most of the cases was not accurate, again, specifically due to multipath and signal reflection. So you can see that sensor errors smooth the GPS noise to improve the positioning. Not only that, but also it bridges the signals bridges the navigation inside the tunnel by providing continuous navigation. The third one is for tethered application, and I will share with you the results through a short video. In the left-hand side, show a 2D projection of navigation in downtown Detroit, while the right-hand side shows a 3D representation showing the difficult environment and the difficult environment for GPS. In most of the cases, GPS was not available at all, right? And and in this case, we have actually 3 accelerometers. Actually, sorry, 1 single gyroscope, 2 accelerometers, and the velocity sensor from the vehicle, plus a GPS receiver. You can clearly see that the red line showed the sensor or the micro machine sensor results, while the green one was the results from $40,000 navigation grade sensor. And of course, you can see that in almost most of the cases, the sensor technology was fitting exactly on top of the $40,000 system. My last slide is related to what can we achieve in real time again for vehicle performance. And I'm showing that through a table. And the best way to show the sensor performance is through periods of signal blockage. So the following table summarizes, the performance of the horizontal performance and vertical performance of the system over different periods of GPS outages up to 10 minutes and a travel distance of about 80 kilometers. The horizontal drift of the inertial sensor in this case was about 100 meters, which is less than 1% of the travel distance, and vertically is about 9 meters. The reference in this case was $100,000 reference IMU. Of course, you can see the promise of inertial systems again for car navigation. So I hope with this presentation that I leave you with the following messages. The first one, of course, MEMS sensors have shown the promising performance for today's applications for indoor and outdoor applications. MEMS inertial navigation system, of course, will continue to improve with advances in both the software and hardware, leading to widespread of many other consumer applications such as games, location-based services, and augmented reality. So this is just the start of how inertial sensors, specifically micro machine sensors, will penetrate many new markets to come. Back to you, Mike.
Nasser, that was terrific. Thank you so much, and a great video. Really, pictures worth 1,000 words. That really drove it home. Folks, we got a lot of questions we're going to get to. We really appreciate your attention and interest, but we now want to ask you for your participation in our final poll. So if you'll just choose one, after watching the webinar and what we've heard today, would you say achieving a hybrid positioning solution that meets your requirements seems likely to be easy, number 1, number 2, moderately challenging, 3, very difficult, or 4, impossible? And I know that our panelists will be very keen to see what the votes are. So 2% of you think it'll be easy, 60% moderately challenging, 36% very difficult, 2% impossible. So I guess the folks who thinks it's easy and impossible cancel each other out, and we have someplace in between. Well, thank you very much for that. Now, for additional information, and we'll send you all of this in the follow-up email, how to get a hold of Brock or Farshid or Tony or Nasser is all on the screen there. We'll make sure that in the follow-up email with the link to the webinar, you'll have this. And also, for our sponsor, Spirent, to learn more, you can go to www.spirent.com/positioning or to globalsales@spirent.com, and there's their phone number. Again, we'll get this information out to you. Well, let's get started with some questions. And gentlemen, welcome back. And I have a question here for you, Nasser. It's how critical is Wi-Fi? It's a two-part question. How critical is Wi-Fi to indoor positioning, and can Wi-Fi be totally discarded since you have sensors and GPS?
Well, thanks, Mike, for the interesting question. I believe definitely that the use of Wi-Fi or other indoor wireless positioning methods will depend on the application and, of course, on the availability of these wireless systems. I mean, the trusted positioning data fusion I show you uses these updates if available, but can't also operate without Wi-Fi, as I have shown in some applications. We also show that indoor positioning with sensor only, but of course with sensor only you will experience a drift that is largely dependent on the quality of the sensor being used. Without low-cost sensors, with low-cost sensors, I show you that we can achieve about 1% of the travel distance for vehicles, and in many other tests we did, we show that we can achieve about 5 to 10% of distance travel for pedestrian. So this in principle translates into, few meters or tens of meters after few minutes without any wireless update. I mean, this might satisfy some applications such as E911, but for definitely longer time periods, Wi-Fi updates are useful to constrain the drift of the sensor-only solution.
Thank you. First sheet, here's one from Dean. What is the refreshing rate of Skyhook's database? Is it monthly or annually or more?
Actually, the refresh rate for us is the entire system is refreshed every week, but it can be much faster, like a day. We don't have really higher resolution than a day now. We didn't feel that it's required, but yeah, as I said, the entire system is get updated at least every week.
Okay. Brock, why don't you take this one? Could you talk about the need for simulation of these combined GPS Wi-Fi systems?
GPS Wi-Fi, yeah, definitely. The greatest part about simulation, I think, is that you can take some difficult situations that might be encountered in the real world, like for instance when you're going from outdoors to indoors, or in an urban environment, or where you've got going under a bridge, and you want to see how you can seamlessly go between a device using Wi-Fi and GNSS and other technology. So when you can simulate those, you can repeatably create those scenarios, and you can test your technology to make sure it works well, and you can adjust your technology and find out whether you actually made an improvement or not.
Thank you. And Farshid, this is for you from Vamsi. Could Wi-Fi support E911 positioning?
I guess the question is, does it do it by itself without any help? You have to actually remember that Wi-Fi positioning works in the places that people are. But if you go to like interstate highways, Wi-Fi positioning doesn't work. So Wi-Fi positioning combined with GPS can satisfy those requirements. But Wi-Fi positioning by itself can only satisfy those requirements within urban environment.
Great. Brock, here's one for you from Martin. Do current cell towers or future towers align themselves close enough in time or to time to be used for time of arrival ranging?
Yeah. One important thing about time of arrival ranging is that it requires a network to be synchronized, and the networks like CDMA do have that. It's not as synchronous in UMTS, and that's been a challenge. For LT networks, there is an option for synchronous, but yes, they are synchronized enough, and therefore the time ranging measurements by the device can be used to accurately locate them.
Great. Farshid, here's one from Zahar. When I hear continuous feedback, stochastic system, and data mining, I get a sense of heavy computational burden. The question is this true, and how do you compensate for this?
Everything that we do on analysis side has been done offline. So that's true. It's computationally complex. We don't do it on users' devices, but it's not terribly hard, and it's not extremely complicated. So I can say below 20, 30 servers handles the entire system, as I mentioned, as I defined.
Okay. And Tony, here's one for you. This is from Samuel. How about GPS receivers that can isolate reflected signals?
Yes. Well, we'd love to have one, I guess. Right now, because of the signal structure, we can't unravel signals that are less than about 150 meters extra path length, and that's to do with just the code rates and the signal structure. There are, however, in modernized GPS and Galileo, better signals coming that will allow us to do that a bit better. So we're looking forward to those.
Terrific. And Steve, I have you back, correct?
Yes, that's right.
Thank you. Did you want to comment on what Brock said about that question before on current cell towers or future towers? I know that was also directed for you.
No, I think Brock's answer was very complete. Certainly, the key thing with being able to combine any technologies in the simulation is to be able to test the efficacy with which those solutions are blended, and particularly where you've got partial solutions, the ability to present all of the those signals of opportunity, if you like, coherently is important, and that's what you can do with a combined simulation system.
Thanks, Steve. And Farshid, here's one for you from Tugril. Does indoor accuracy using Wi-Fi depend more on the number of APs or the complexity of the building indoors? I don't know if that's supposed to be APIs or what, but I think you know what the question is.
I think if I understood the question correctly, accuracy indoor depends definitely on number of anchor points, and it also depends on the environment both. And if question is which one is more important, it's hard for me to say anything. In terms of number of access points, definitely if you do have more metals and need more resolution, more access points can help.
Thank you. And last one before I give some final housekeeping tips to everybody on the next steps. Nasser, this is for you from Iran. What are the sensors used in door positioning? Can you answer that?
Actually, there is many sensors actually in the market nowadays. I mean, for example, many of these current smartphones include MEMS sensor from STMicro, VTI, InvenSense. For example, the sensors are used in the type A test includes also, barometers from Bosch and magnetometer from Asahi Kasai. But there is lots of sensors right now in the market, including some have been already used. And I encourage the audience, if they have any question, they can contact me and can give them exactly the exact models of the sensor we used in some of these tests.
Thank you so much. And I can't believe the 90 minutes is just about gone by. There's been a tremendous amount of interest in today's webinar, and we really are thrilled with the questions. And as I've said at the top of the webinar and several times throughout, we absolutely promise to get a subject matter expert back with the response to your questions. There are more questions than we had time for answers for, so hopefully the value of what we presented today really met your interest and expectations. And to that, thanks so much for joining us, and special thanks go to Tony Haddrell and Steve Hicklin in the UK, Farshid Al-Zaida, Nasser Al-Shimi, Brock Butler, and of course our sponsor and co-host, Glenn Gibbons of Inside GNSS. And special thanks to our producers, our logistics producer, Patty Van Hooser, and content producer, Lori Dearman, for all of their behind-the-scenes work and collaboration and working with our panel. Most importantly, we thank you again for your time. And as your moderator, this is Mike Agron wishing you a great rest of the week, and we hope to see you soon on another Inside GNSS webinar. Bye for now.